Good morning. Chapter 1: Mathematical Modeling, Numerical Methods, and Problem Solving. The primary objective of this chapter is to provide you with a concrete idea of what numerical methods are and how they relate to engineering and scientific problem solving. The specific objectives and topics covered are learning how mathematical models can be formulated on the basis of scientific principles to simulate the behavior of a simple physical system. Number 2, understanding how numerical methods afford a means to generate solutions in a manner that can be implemented on a digital computer. Number 3, understanding the different types of conservation laws that lie beneath the models used in the various engineering disciplines and appreciating the difference between steady state and dynamic solution of these models. Number 4, learning about the different types of numerical methods we will cover in this book. A simple mathematical model. A mathematical model can be broadly defined as a formulation or equation that expresses the essential features of a physical system or process in mathematical terms. In a very general sense, it can be represented as a functional relationship of the form, where the dependent variable is a characteristic that usually reflects the behavior or state of the system. The independent variables are usually dimensions such as time and space along which the system's behavior is being determined. The parameters are reflective of the system's properties or composition, and the forcing functions are external influence acting upon it. The second law can be recast in the format of equation 1.1 by merely dividing both sides by m to give, where a is equals to f over m, where a is the dependent variable reflecting the system behavior, f is the forcing function, and m is a parameter. Note that for this simple case there is no independent variable because we are not yet predicting how acceleration varies in time or space. Equation has a number of characteristics that are typical of mathematical models of the physical world. It describes a natural process or system in mathematical terms. It represents an idealization and simplification of reality. That is, the model ignores negligible details of the natural process and focuses on its essential manifestations. Thus, the second law does not include the effects of relativity that are of minimal importance when applied to objects and forces that interact on or about the Earth's surface and velocities and on scales visible to humans. Finally, it yields reproducible results and consequently can be used for predictive purposes. For example, if the force of an object and its mass are known, equation 1.3 can be used to compute acceleration. To illustrate a more complex model of this kind, Newton's second law can be used to determine the terminal velocity of a free-falling body near the Earth's surface. Our falling body will be bungee jumper, or in this case, a model can be derived by expressing the acceleration as the time rate of change of the velocity dv over dt and substituting it into equation 1.3 to yield, where dv over dt is equal to f over m, where v is velocity in meters per second. Thus, the rate of change of the velocity is equal to the net force acting on the body normalized to its mass. If the net force is positive, the object will accelerate. If it is negative, the object will decelerate. If the net force is zero, the object velocity will remain at a constant level. Next, we will express the net force in terms of measurable variables and parameters. For a body falling within the vicinity of the Earth, the net force is composed of two opposing forces, the downward pull of gravity, which is Fd, and the upward force of air resistance, which is Fu, where F is equals to Fd plus Fu. If force in the downward direction is assigned in a positive sign, the second law can be used to formulate the force due to gravity as Fd is equals to mg, where g is the acceleration due to gravity, which gravity is 9.81 meter per second squared. Air resistance can be formulated in a variety of ways. Knowledge from science of fluid mechanics suggests that a good first approximation would be assumed that it is proportional to the square of the velocity, where Fu is equals to negative CD times V squared, where CD is a proportionality constant called the drag coefficient by kilogram per meter. Thus, the greater the fall velocity, the greater the upward force due to air resistance. The parameter CD accounts for properties of the falling object, such as shape or surface roughness that affect air resistance. For the present, CD might be a function of the type of clothing or the orientation used by the jumper during free fall.
Conservation laws in engineering and science. Aside from Newton's second law, there are other major organizing principles in science and engineering. Among the most important of these are the conventional laws. Although they form the basis for the variety of complicated and powerful mathematical models, the great conservation laws of science and engineering are conceptually easy to understand. This is precisely the format that we employed when using Newton's law to develop force balance for the bungee jumper. Although simple, embodies one of the most fundamental ways in which conservation laws are used in engineering and science, that is, to predict changes with respect to time. We will give it a special name, the time variable or transient computation. Numerical methods covered in this book. We choose Euler's method for this introductory chapter because it is typically of many other classes of numerical methods. In essence, most consist of recasting mathematical operations into the simple kind of algebraic and logical operations compatible with digital computers. Figure 1.6 summarizes the major areas covered in this text. Field: chemical engineering, device, reactors, organizing principle, conservation of mass, mathematical expression, mass balance, input-output, over a unit of time period, change of mass is equals to inputs minus outputs. Civil engineering, device, structure, organizing principle, conservation of momentum, mathematical expression, force balance. At each node, summation horizontal forces, f of h is equals to 0. Summation of vertical forces, f of v is equals to 0. Field: mechanical engineering, device, machine, organizing principle, conservation of momentum, force balance, upward force, downward force. M d squared s over dt squared is equals to downward force minus upward force. Electrical engineering, circuit, conservation of charges, current balance, each node, current. A. Part 2. Roots and optimization. Roots: solve for x so that f of x is equals to 0. Optimization: solve for x so that f x is equals to 0. Part 3. Linear algebraic expression. Given that a's and b's, solve for x. Part C. Curve fitting, regression. Part 5. Integration and differentiation. Integration: find the area under the curve. Differentiation: find the slope of the curve. Part 6. Differential equation. Given dy over dt is equals to change of y over change of t is equals to f of t and y. Solve for y as a function of t. Y plus 1 is equals to y plus f of t and y change of f. That's all for chapter 1. Thank you.